Hello everyone, in this video I am going to visualize the concept of addition of two waves with their E vectors in two perpendicular directions. In particular, what state of polarization results when we combine two vectors in perpendicular directions. State of polarization describes the pattern and orientation of polarized light. Pattern in the sense it can be a line, it can be a circle, it can be an ellipse. Orientation implies what angle does this pattern make with the axis system. There are two important questions which you have to understand when dealing with polarization. How to construct a required state of polarization, and the second question is how to measure the state of polarization of a given light. Now these two questions are important both from a theory as well as experiment point of view. In this video and couple of more videos in this series, I'll be dealing only with the theory part, and later I'll be showing how to answer these questions experimentally using this knowledge. When we talk of polarization of light, three components are a must to understand the polarization: the polarizer, a quarter wave plate, and a half wave plate. I'll be dealing with these components one by one after this video. The question we are asking is, when two light waves, now I am talking of two light waves because this concept of polarization is mostly useful for polarization of light. Hence I will be talking of light instead of waves, or when I say wave I imply light wave or electromagnetic wave. So when two waves of same frequency, same polarization, moving in the same direction and same region of space, and if their electric field vectors are collinear, their addition results in interference, and if the electric field vectors are perpendicular, different states of polarization can be realized, and this is the concept for today's video. This is what we are saying. Ex and Ey are two plane waves oscillating in two perpendicular directions: E0x cos kz minus omega t plus phi x and E0y cos kz minus omega t plus phi y. In textbooks, phi x is taken as 0, and instead of phi y it is only written as phi, so that becomes the phase difference between these two waves. The simplification leads to a generalized ellipse equation. For those who are interested, please go and check one of my videos in oscillations playlist where I have derived this. The treatment is identically same. There it was oscillation of a particle, here we are talking of a wave, and in a sense this is identical to that treatment because this also deals with one point in space as a function of time. So the electric field, the resultant electric field looks like this, and if 2 alpha is the angle made by the major axis of the ellipse, tan 2 alpha looks like this. So in effect, the resultant polarization depends on E0x, E0y and phi y and phi x. That is to say, the state of resultant polarization wave depends on phase difference and relative amplitudes. The most general case being elliptical. This results for all angles of delta and all relative amplitudes except for 0 to pi, pi by 2 and 3 pi by 2 radians. When the amplitudes are equal and phase difference is either pi by 2 or 3 pi by 2, it results in a circular polarization, left or right, and when phase difference is 0 or pi, it results in a plane polarized light, and amplitudes can be of any ratio. Now when it comes to circular and elliptical, the sense of rotation is important, and to distinguish that we have sine delta, that is, if sine of phase difference is greater than 0, it is referred to as left polarized light, and if sine of delta is less than 0, it is referred to as right polarized light. Now this right and left, it is important to mention in which direction the light is moving, and from where the light is being observed. So here the light is coming out of the screen, and I am sitting in front of the screen, and if I view that light, how does it look? Let's come to the visualization window. It is heavily populated, so let me spend a minute to describe the things. On the left we have parameters related to the wave, that is, I can give the wavelength and the speed, and down here I can give the polarization properties, that is E0x, E0y, phi x and phi y. And here I have three visualizations which I will show one by one, and on this right there are the properties of the wave, different properties of the wave. The color schemes which I am using are two. One is for x and y direction. Blue is used for x oscillations and red is used for y oscillations. And for sense of rotation I will be using magneta and green counterclockwise, that is left is magneta and clockwise or right is green. To start with, let me give some numbers. E0x is 2, phi x is 0, E0y is 2 and phi y is 0, that is delta phi is 0. So let us see how does this wave look. So it looks something like this, and this is the three-dimensional view of the wave. The z-axis is coming from the monitor. You can see this is the z-axis, 0 here and increasing out of the monitor. This is x-axis going from left to right and y-axis going from bottom to top. Now the important thing in this visualization is, or in this concept is, any state of polarization can be decomposed into two linearly polarized component waves in perpendicular direction. Vice versa, given two linearly polarized component waves in perpendicular directions, we can synthesize a desired state of polarization. So it depends on E0x, E0y, phi x and phi y. So this wave, let us look what is the Ex. So this is the Ex in this plane, and similarly Ey. So when this wave propagates, how does it look? Let us see. So the wave is coming out, and this line over here shows how does the electric field magnitude changes as a function of time. So as such, this looks very complicated and it needs either a color scheme or a detailed distinction between three components. Hence, in textbooks we also find this Ex and Ey being plotted separately. That is, Ex versus Z is plotted like this. So this is Ex versus Z. It becomes a two-dimensional graph because it is oscillating in a single plane. Similarly, Ey, this is Ey, and as we can see, they are in phase. So when Ex is maximum, Ey is maximum, Ex is minimum, Ey is minimum. So here we can see, let me remove Ex and Ey now from here. So either this wave can be decomposed like this, or these components will lead to this kind of a state of polarization. While these two graphs are great to understand the exact state of polarization, it is the polarization vector diagram which is most often used and makes it very easy to understand the concept. So what does it do? This line over here, magnetic line, is the magnitude of the field as a function of time. This will be drawn separately in this window. So on the x-axis is Ex and on the y-axis it is Ey. So this particular line of this, because it is oscillating in a plane, is drawn separately, and the arrow shows the direction of the field. So in most often the polarization, these graphs are given, but most importance is given to this graph because for understanding and analysis this is easy and useful. So let us see the component waves also, because the individual components are also vectors, and this forms the resultant of two components. So the blue is Ex, red is Ey, and their resultant is what we see, something like this. So black is the resultant, blue is the Ex component, and red is the Ey component. They are in phase. So let us look at the time slider. As Ex decreases, Ey also decreases. When Ex becomes negative, Ey becomes negative, and they change in tandem. Let's look at this. So at any instant of time, this is as a function of time, Ex and Ey look like this, and the individual Ex and Ey components looks like this, and the resultant wave is something like this, the 3D wave. So since Ex is equal to Ey, the resultant makes an angle of 45 degrees with the x-axis. If Ex and Ey ratio changes, the angle would also change. So as Ex is more and more Ex would mean the angle which it makes with x-axis becomes smaller and smaller. 3 and 1, so E0x is 3 times greater, hence it makes a smaller angle. Let me try much more. So it's almost in the x direction, and if it is made 0, it becomes x polarized light, or vice versa. The Ex is 0 at all z, and Ey is what remains. So this visualization I had done in my last video also. If you are interested, please go back and check that video. One can think of other angles